Thank you so much for the introduction, Sarah. I'm one of those geoscientists that you were talking about. Today, I'm really going to focus in on how we can actually use machine learning to think about and quantify and communicate uncertainties. I think I've been able to dial in a few times to hear some perspectives on AI from the Oxford SEG students and from Sean Barker and others. And today, I want to build in on that a little more. I'll show you how this plays out in a pretty fundamental step of ore characterization by simply identifying mineralogy. So I really liked what you were saying about certainty and uncertainty, right? Those are kind of different ways of framing some similar problems. And to understand why this step of like thinking about mineralogy is so consequential, I want to start off with a problem that Frenzel and colleagues laid out very clearly. Ore deposits, we know, are quite geologically complex. They're products of multiple events. We have thermal gradients, metamorphic overprinting, weathering. And what that means is that if we think about the mineralogy and texture across a deposit, there's pretty significant variation. Difficulty is that we can only ever sample a pretty small volume or a fraction of the volume through drill cores if we're lucky. And so we're always working with incomplete information. You can kind of visualize this with the maps that are shown on the right. Panel A shows the copper grade across a deposit, which is kind of our best estimate at things. But if we look at panels B and C, what we see is that these realizations of copper recovery look almost nothing like the grade map, and that's because recovery isn't necessarily controlled by grade. There are other factors going into it. And what I think Frenzel and colleagues point out is that more than half of new mining operations fail to reach their projected performance targets, which is a bit of a staggering statistic. And this is the principal reason of why. You have really strong variability, but it's not necessarily being characterized. And that really starts at the most basic level of thinking about the mineralogy. And these labels are what currently lack some strong uncertainty assessment. So everything kind of starts with the minerals. And accurate mineralogy really underpins every primary ore property. If you're trying to constrain and reconstruct a pressure, temperature, history path of a magmatic system or characterize an ore deposit for processing, both of these kind of start at the step where you need to know what minerals are present, what abundances, what are the grain sizes, what are the compositions, and what really is where I'm focusing in is that we want to kind of develop these open source tools for doing this classification rapidly at scale and with some sense of uncertainty and some quantification of uncertainty. So why does this problem kind of need some focus now? I would say that two things have really changed that have caused a data revolution. So instrumentation has gotten a lot faster. These modern EDS detectors or energy dispersive X-ray detectors can kind of map these entire thin sections overnight. You can throw four thin sections into an SEM and come out with millions of pixels of full oxide chemistry. At the same time, there are also these geochemical databases that have tens of millions of analyses that aggregate a ton of analytical work from labs around the world. And so for both of these are really exciting developments, but the data are now arriving more rapidly than we can actually classify and handle it. And so you can collect a million analyses overnight and be stuck manually checking all of these mineral assignments or using proprietary software that gives you a label with no indication of how confident it is. And so this is what leads me to the project that I've been working on for the past 2 years or so. I've been building this open source package called mineralML aimed at answering some of these fundamental questions. So what minerals are in a rock, at what abundances, and with what compositions. So this code package kind of handles both tabular and mapped data. For tabular data, you're working with a spreadsheet of oxide analyses, so you get back what you want back is a predicted mineral, a prediction score, and uncertainty on that score itself, along with these sorts of two-dimensional visualizations to think about how your analyses relate to the distribution of minerals it was trained on. For the map data instead, the pipeline generates these phase maps, modal proportions, and stoichiometric subclassifications. So if you're working with feldspars, you can take all of your feldspars and immediately plot the compositions on the ternary. I'll walk you through the architecture and show how we can actually use machine learning to get at these uncertainty and then show some validation results. I know this is a bit of a maybe an unfamiliar sort of slide, but basically what we've done here is design this neural network. Neural networks are essentially really flexible mathematical functions that learn patterns from examples. So if you show it millions of analyses where you already know the label, so let's say this is an olivine, this is a plagioclase, this is a CPX, it learns to recognize the chemical fingerprint of each one. And once trained, you can essentially apply it to new analyses that it's never seen, and it tells you what mineral it looks like. First bit of this neural network is a classifier. So you feed in these sorts of oxide compositions. The network transforms them into a series of layers and what we want back is ultimately a predicted mineral and score between 0 and 1. A high score close to 1 would mean that it's really confident, whereas a low score means, oh, I'm not actually exactly sure what mineral this is. And the key design choice that actually lets us get at uncertainties is this variational layer that's labeled in part B of this figure. The weights essentially of this neural network are parameterized as distributions rather than fixed values, which is what gives us meaningful uncertainty estimates on each prediction rather than just a point answer. I won't focus too much on this because it's not exactly relevant to uncertainty as much, and I don't have quite the time. But if you're interested in learning more, I'll give a bit of a shameless plug for this manuscript, which is currently in review. The preprint is on Earth Archive, and you can go check that out. But essentially, this design choice of parameterizing these as weights or as distributions rather than single fixed answers for each input mean that the network can learn a range of possible answers and sample from that range at the time of prediction. The spread of these predictions is essentially our uncertainty estimate. So if you have a confident prediction, in blue, you essentially might see that all of the samples agree. So all of the passes through the neural network return the same answer. Whereas if you have an uncertain prediction, you might have a lot of disagreement across different passes. And what's useful about this is that the uncertainty essentially tracks data quality automatically. We did a dwell time or acquisition time experiment here at Berkeley where we essentially were collecting spectra at 1 millisecond versus 50 milliseconds. And what you can see is that in the beginning, there's a lot of checkerboarding, there's speckling in the predictions of the neural network that we actually have. And correspondingly, the prediction scores kind of have this really wide spread. Whereas when we start acquiring for more time, this map really cleans up. You can see that the prediction scores also tend more towards the yellow bit of things. It's closer to 1. So the neural network is more confident in this. This is essentially providing us, the neural network is telling us where we can trust it without additional measurements and where maybe we want to re-examine the outputs with these prediction scores. And so we can use this as a flag for determining what regions of a phase map might need a second look and which do not. And so I think that uncertainty signal I showed you is really just one piece of a larger picture. I want to be precise about the different types of uncertainty at play here because they all require some different responses. First branch is aleatoric uncertainty. So this is what's irreducible. Minerals exist on solid solution series, they're zoned, they're altered, and to some extent, there are compositions that sit between oxides that are genuinely ambiguous. So if you think about the clinopyroxene and amphibole, there's a lot of overlap in in their concentrations, and no amount of better data will really resolve that. And so this is reflected essentially in that P bar value that kind of tells us how confident the neural network is in that prediction. We also have epistemic uncertainty, so what the model genuinely does not know. If you run in a phase that wasn't in the training data through this classifier, it'll appear as an outlier in latent space and carry a really high sigma p bar value. And that's what the model is saying. And I haven't seen this before, essentially. Treat this analysis carefully. That signal is usually absent from most considerations of this. And lastly, I think what this really comes down to is how these kind of uncertainties kind of propagate and combine. When we have these point estimate labels that we maybe are using less critically, that really influences downstream models and downstream decisions. So we kind of have to consider both of these sorts of uncertainty before moving forward. I'll show some pretty maps now. So these are some examples of testing that we've done on some intrusive rocks and extrusive rocks. But essentially what I'm showing here is that we've tried to basically validate this method on looking at these different types of rocks. And in this example, we're comparing both compositional data on the right from EDS to basically structural data from EBST. So these are some of the maps that we've generated, and what you'll notice is that mineralML is returning maps that basically look are within 2 to 3% uncertainty of what we get, what sort of information we get back from the structural crystallographic information provided by EBST. Lends a lot of confidence to this model. This is another pretty rock, but you can kind of see how these different methods provide different sorts of information. So EBSD is looking at crystallography, and so non-crystalline phases like glass, which is indicated in yellow here, aren't identified. And that's kind of the value added information provided by chemistry. So I'll just wrap things up now, but I'll give a little pitch for mineralML. It's entirely open source and reproducible with the data and code that are publicly available. I've developed Jupyter notebooks and abundant documentation for running this code, so you could go run it yourself today if you are so inclined. I'm really interested in testing things out with different modes of data. So far I've used SEM EDS data, but I anticipate that there might be some extensions to XRF and to other maybe methods that are more commonly used in core logging. And we have a collaboration underway to kind of test these things out. Um, Lastly, I'm a second year PhD student. This has been a project that's been in development for a little bit, but I've started building this model aimed at igneous systems, but this is sort of the first iteration of the model. We have targets moving forward to develop this, expand this model to kind of metamorphic phase assemblages and more ore relevant phases. Specifically, I'm going to be working on sulfides in the next few months. And that's what I have planned moving forward into the summer and through the fall. So if anyone has samples of interest that they'd like to test or specific mineralogy that might be useful, please do reach out. And with that, I think I will stop sharing.
Brilliant. Sarah, thank you so much. That was absolutely fantastic. Thank you very much for that. Now, just quickly, for people who aren't geoscientists, etc., on the call, some of you might have been going, wow, pretty pictures. Not sure what all of the words were referring to. Don't worry, not even all the geoscientists in the room would have come across all the words because that was absolutely brilliant what you've been putting together there, Sarah. I guess if we take a step back and we say, I think there's often the assumption that a geoscientist, whatever, should be able to look at a mineral and go, right, I know exactly what that is. But that's not the case, is it?
That is absolutely not, especially when you're a I think the traditional way of doing a lot of this is looking at thin sections, right? And it takes a lot of like domain knowledge and expertise to kind of get to a point where you can be confident about that. And even so, when you're working with wonky compositions and things that you might not see as frequently, it takes quite a bit of time to get to that point where you can actually identify these things. So we've really adapted this and used this also as a teaching tool. So
Mm.
for a lot of students who are using the SEM for the first time, you're kind of shooting these electron beams at different minerals that you see that are pretty, but you don't necessarily know exactly what it is before you analyze it. And so what we've observed is that a lot of the time it's difficult to kind of distinguish these minerals even when you have compositions. And this is really where this code package comes into the mix.
Yeah, no, that's so cool. I mean, and so that's the case there where obviously an SEM is basically a super duper microscope and you can get that chemical composition, can't you, coming back. So you go like, aha, okay, it's got that much
Yeah.
iron or magnesium or whatever in it. I know what kind of mineral that's probably going to be. Now you said, does anybody have any rocks in your talk? Well, unfortunately for you, you've got Richard Harrington on the line here. Who I don't know might have the entire Natural History Museum here in London at its disposal. And if you haven't already seen it, and this is for everybody, last year we made a documentary about raw materials, and it was based in the Natural History Museum. And some of the shots of the mineral gallery there in the museum are truly phenomenal. I think they almost brought a tear to Richard's eye when we rewatched it again as part of the one of the lunchtime sessions yesterday. But Richard's asking Sarah. He first says, great talk. And how does your process deal with mineral polymorphs? Can we incorporate structural mineral data in some way?
That's a great question, Richard. Thank you. I will say that that's exactly what we kind of were targeting with the EBSD. So these maps were basically collected by a postdoc in our lab, Charlie Gordon, who is an expert in EBSD. And so EBSD provides that sort of structural information that you're mentioning. For these maps, we're basically collecting both of them at the same time with a 50 or with some dwell time that's specified by what the uncertainties are and how rapidly we can kind of get a diffraction pattern. So we are trying to combine exactly that to kind of aim at this polymorph question because we we can't really deal with that with just chemical compositional information. They have exactly the same chemistry but different structures, and that's kind of what the EBSD information is attempting to add.
Brilliant. So I guess that's using like different modes of data collection to get different
Yeah.
information, isn't it, about the minerals, and then go, okay, right, so I've got this chemical data, I've got more structural data, so that's therefore giving me a more confidence in what it is that I'm actually looking at. Is that
That's
correct?
exactly right. And that's kind of how we aimed at validating this method to say these two methods agree. So we can be quite confident that the neural network is returning something sensible. So it's a big part of our validation step in all of this.
Yeah, no, I love this because I think, one of the, I mean, it's not a very funny joke. I mean, I find it mildly amusing. Within the world of geology and raw materials is you say, right, well, one rock, two geologists, three answers. Because as well, I think the engineers of the world always accuse geologists of being, well, it's an arts subject, which of course I'm sure will surprise many of the social scientists and the humanities people here on the call because they might not consider geology as being an art. But I think this is something where being able to accept the fact that we don't necessarily know what something is, but your tool is then bringing that robustness to the table where we've got that ability to use machine learning, etc., to say, well, no, I feel a bit more confident about what it is that I'm looking at. Now, Sarah, there are more questions coming in the chat. You've got Jay, who's given you his email address and said, yes, please, let's
Awesome.
go play. Excellent. Also, I think there are other questions coming in, but my WhatsApp has just blown up with the entire team behind the scenes discussing what's their favorite mineral. So I don't know, team, if there are any questions in there, because all I can see is Aileen just writing pyrite about 1,000 times. And not just that, she's now discussing what particular type of pyrite that's in there. Aileen, do you want to say anything really quickly?
Um, no, sorry, you caught me off guard there. Yeah, I in a very different life would have done a PhD on geochemistry of sulfide deposits, particularly in Ireland, which are kind of like a transition between Mississippi Valley type and what people used to call SEDEX as well. So that's a very technical thing for anyone who's not aware of deposit types, but basically they're supposed in sedimentary rock. But one of the things that we were looking at was around pyrite and using it as a potential vector toward mineralization as well, using geochemical maps. And one of my colleagues who's actually going to be talking at the Gordon conference as well, Claire, is found some really interesting like Raman maps and Raman variation, looking at different things like marcasite and pyrite and trying to tell them apart because often they're kind of ignored. So I don't know if you've ever looked at like other technologies like Raman or other kind of ones like that before.
Yeah, I haven't worked directly with that yet, but we do have a ramen lab at Berkeley. My advisor, Penny Weezer, runs that and has worked a lot in looking at basically composite ramen applied to fluid and melt inclusions.
Yeah,
But
awesome.
we've actually been doing some testing recently to look at kind of different sorts of minerals and how we can use ramen to identify them. We've mainly been
Yeah.
looking at apatite so far.
Oh
But I
yeah,
know there are
okay.
some difficulties about like orientation of the sample. So you kind of have to find ways to kind of orient your sample in all kind of crystallographic directions before you sort of are able to kind of match spectra exactly. But that's definitely a line of research that I'm quite
Yeah.
interested in. And it would be cool
Yeah.
to work with that a bit more.
Yeah, it seems like there's a lot of potential that way for sure. Thanks,
Yeah.
there.
So despite appearances, this amazingly is not a conference on mineralogy, for example, or petrology, or even the ins and outs of different types of analytical techniques. It could be, but actually it's hugely important. And thank you so much, Sarah, for kicking us off this afternoon with all of this, because this is really exciting research. Because the more we can actually understand about those rocks, the more we can understand about where there may be minerals and metals in the ground, but also other things that might be interesting to extract. And that is where one of the ways in which we do enhance our certainty or our confidence in terms of what might actually be in the ground, but also what might be going on with regards to water, other aspects with regards to the environment, and of course, going on into human beings as well. So, with that, Sarah, thank you so, so much. It's a brilliant way to start off this session. Round of applause, everybody, for the fabulous Sarah Shee. Absolutely brilliant. Thank you, mate.